doing the same thing. I think that this is the easier method, personally. Okay, so we've got another reaction we want to look at here, which is iron ions reacting with, does anyone know what that ion's called? It's actually called dichromate. Dichromate, because there's two chromiums in it. So this is iron reacting with the dichromate ion to give us different iron ions and chromium ions. Now, the first thing you're going to note is obviously where'd the oxygen go? Well, we haven't balanced it yet. But this reaction does happen. You can turn iron 2 plus ions into iron 3 plus ions, and you can turn the dichromate ion into chromium ions in acidic solution. This reaction will happen. That should be 2 plus. That's a typo. I'm ashamed. I blame. Who do I blame? I don't know. Sure. Yeah, I support that. Okay. So what we want to do today, instead of what we could do this the way we did it yesterday, and it will work totally fine. All right. And if time permitted, I would actually do that first to show you. But time doesn't permit. So we're just going to jump right in and say, instead of what we did yesterday, I want to show you another method, which is we're going to break it into half reactions. All right? And when I say half reactions, what I mean is we're just going to focus on the two things. This isn't always the best way, but I think in a case like this where we really clearly have, you can see the two reactions here, which is iron is changing, and then dichromate is becoming the chromide ion, right? The chromium ion, chromium 3 plus ion. So we're going to break this down. We're going to say part of this reaction is iron 2 plus is becoming iron 3 plus. Now for that to happen, what must iron be doing? Which one? Okay, so it must be losing an electron, which means an electron must be a product. Does that make sense? If it's losing an electron, then the electron is the product. We'll make a little note of that. Iron loses an electron. So it's a product. Is this an oxidation? Let's try that again. Is this an oxidation reaction or a reduction reaction? Oxidation. Okay. That must mean that the other reaction must be a reduction. So let's look at it. Cr2O7, 2 minus, is going to become Cr3 plus. Now, this must be a reduction, but it's not immediately obvious yet how. So we're going to hold off. Does that make sense? I put this electron in up here because it's easy to figure that out. Is that fair? This bottom one, we're going to hold off. Is that fair? Because can you eyeball that and quickly say how many electrons it's gaining or losing? I can't. So those are our two half reactions. Now, we're going to make sure the elements balance. Iron 2 plus becoming iron 3 plus. Do we have the same number of iron atoms? Yeah, so that's good. And I shouldn't have actually written that electron yet. I forgot I was going to do that with you. I get excited. Team, I get excited. But whatever, we'll write it again. We know it's there. Doesn't actually matter. Cr2O7, 2 minus, reacts to form Cr3 plus. Do we have the same number of chromium ions there? No. So what should I do? Put 2 there. Does that make sense? You got to balance the half reactions. We're not going to worry about oxygen yet, right? So then we're going to get the electrons in there. And again, Fe2 plus becoming Fe3 plus. It was very easy to say that that just involves losing one electron. But if I didn't know that, what would I do? Well, I would say iron goes from having an oxidation number of 2. to having an oxidation number of 3. That's a delta of -1. Therefore, 1 electron. Does that make sense? Is that cool? Okay. Can we do the same for the dichromate ion becoming the chromium 3+ ion? Cr2O7 2- is going to yield 2 chromium 3+ ions. Well, what is oxygen giving us here? -14. So, what must chromium be giving us? 12. And so each one is giving us 6. Okay, good. And then over here, what is each one giving us? +3, and of course there's 2 of them. So therefore, what's the delta? It's going down by 3, right? And since there's 2 of them, the change is 6 electrons. Does that make sense? How you show it doesn't matter, but it's important since the change is -3. Now, -3, does that mean it's gaining or losing electrons? Gaining or losing? If its change is negative. Okay, so this is gaining 6 electrons, 3 for each chromium, right? Because it's reduced, right? And reduction is gaining. So if it's gaining, do I put the electrons over here or over there? On the right side?
No, on the left side.
That's okay. Which one is it?
Left side.
Left side. Why is it on the left side?
Because it's part of the reactants.
Yeah, because it's gaining them. So it's saying if we take that original thing and 6 electrons, we can make that. Yeah.
So, wait, never mind. I figured it out. Because there's, never mind.
Do you want to say it anyway? Because someone else might have the same question.
I was going to ask why we need 6 because there's 6 on that side and 6 on that side. But then I realized there's actually 12 because we have 2 chromium, not. So I just,
Yep.
I was just about to be like, wait, why do we need this?
Yeah, when you have 2 of them in your reaction, it does make it trickier, right? And how you work your way through that is totally up to you. But you got to kind of make sure that you're accounting for the fact that there's 2 of them. Yeah.
You said the delta of them would be 6, but wouldn't it be 3, like negative?
It's 3 each. Yep. So if you look here, that's what I said. 3 for each chromium. But of course, how many chromiums do we have? 2. So if it's 3 each and there's 2 of them, how many is that? Does that make sense?
Yeah. So
Cool.
we have to, when we're doing the delta, we have to like take into account how many there are.
Yep. Absolutely. And again, how you do that is up to you. Now, for each one of these, we need to balance the charge if it needs to be balanced. So let's look at our first one. Fe2 plus becomes Fe3 plus and an electron. What's the charge over here? It is? +2. Okay. What's the charge over here? +2. Do we need to balance it? Nope. Okay, so we'll leave that be. On the other hand, if we have Cr2O7 2-, and I'm going to put the electrons after it. I like that better. It doesn't actually matter at all. Becomes 2Cr3 plus. What's the charge over here? Okay, +6. What's the charge over here? -8. Is that balanced? No. In fact, it's so unbalanced. What do I need? No. No, careful. How many H pluses? 14. Very good. Does that make sense? They need to be the same. Charge needs to be balanced, right? Not opposite, the same, right? So that means to get this to also be +6 requires 14 H pluses. All right? By the way, you could do it the way we did the other ones and balance the oxygen first. I was taught to balance charge with the H pluses because that goes quicker. So that's just how we do this. And then we'll use H2O to balance hydrogen and oxygen. And it will either work or it won't. And if it doesn't work, then the thing won't balance. So what is the top then? The iron hasn't changed. Fe2 plus is going to become Fe3 plus, and we're going to have that extra electron. And then down here, we're going to say that 14 H pluses and Cr2O7 2 minus with 6 electrons will give us 2 Cr3 pluses. What do I need here to balance it in terms of water? 7 waters. And if this is going to work, that's going to balance both the hydrogens and the oxygens. Does it balance both the hydrogens and the oxygens? Yeah, cool. Now, then the reaction doesn't work. Yeah, if a reaction won't balance, then the reaction doesn't work.
Mr. Rolando, what's a G? Where did that come from? Oh, that's chromium. Never mind. The CR over there at the bottom looks like a G.
Moving on.
Sorry.
So now, what we can do is we can just combine these back into a single reaction. Now, the only thing is, the reaction will only be useful if what cancels? The electrons. So, to combine them, we need the electrons to match. Where will they match? This has 1 electron. This has 6 electrons. So where do you match those up? What's the common multiple there? 6. So what do we have to multiply the top reaction by? And the bottom reaction? Just leave it alone. Multiply it by 1. So then when you go to put them together, just do that. So the top reaction is 6 irons, right? With 2 plus charge. And then we add how many hydrogens? 14. And then a Cr2O7, 2 minus, plus 6 electrons. And those electrons are going to cancel, right? So I'm going to not bother to write them because they're going to cancel on both sides. That's the whole reason we're doing this, right? Does that make sense? And then what's going to go on the right side? 6 iron 3 pluses. And then again, I could write 6 electrons, but the whole point of doing this is that they cancel. But what can I write? 2 chromiums, and then 7 waters. Oh, what am I doing? And then, of course, we should add our states of matter once we're actually finished. It makes no difference to me if you use half reactions or if you use the method we learned yesterday. I don't even on the test or on the exam tell you which one you have to use for any question. My experience in university was that they taught us half reactions and didn't even bother to teach us the other method, I think. Or certainly we always used half reactions. But they're just 2 techniques to get you to the same place. The technique of splitting a reaction into pieces and then recombining it is a useful one to have. But again, it's not the only way to do it. If you had done this the way I taught you in the previous lesson, you know what you would get? The exact same answer. This is kind of nice because you can kind of work in pieces. But what you prefer is what you prefer. To be honest, as an adult, I tend to actually prefer the other way now. And I tend to just do it all in one shot and just kind of go. But this, I think, is easier to do in kind of bite-sized chunks. Which one you pick? Totally up to you. How's that feel? Not too bad? I'm trying to blast through the lesson-y portion of this so we can have a day or maybe even 2 days just to get some practice in. So I know I'm kind of like walloping you, but expect to continue to get walloped. Can we try it in basic solution? Remind me, what's the only difference in basic solution? Yeah, what you're going to recall is that any H plus gets replaced with H2O with OH minus added to the other side, right? Other than that, it's the exact same process, right? But in basic solution, H plus won't stick around. So you just say, oh, that H plus is actually going to be an H2O. But for that to happen on the other side of the reaction, there must be an OH minus. Does that make sense? Is that cool? We're comfortable with that? Okay. Can we try this one? So again, the thing we eyeball here really quickly is that the half reactions are what? And I'm going to just kind of show you, what would your comfort level be? Do you want me to write it out over and over again? Or do you want me to write it and then kind of follow the steps? Because do you see how like in the homework yesterday, I don't actually write the reaction over and over again? I actually find that messier. So can we do that? We're going to write it and then follow the steps. So what's the first half reaction here? S with a charge of 2 negative becoming SO4. So the first thing I'd say is leave yourself some space around it. Does that make sense? Why do I leave space around it? So I can add all the stuff I need to add. Does that make sense? And now let's just go in order. First things first, we need to balance the key elements. Are they balanced? Yeah, they're good. Okay. Nice. Next, we have to do what? Add electrons to balance the oxidation number change, right? So what's the oxidation number here for sulfur? So for sulfur on the left side, it has -2, right? And then what about on the right side? -6? +6. So what's the delta? Going up by 8. Is that oxidized or reduced? Just so we know. It's oxidized. Good. Okay, so that means which side does the electrons go on? Sulfur's losing electrons. Which side do they go on? On the right side. How many? 8 electrons. And I'm going to kind of put that little line in here to show where we got that information. Does that make sense? We got that information because we came up with that. Is that cool? If it's gaining electrons, or if it's gaining oxidation number, it's losing electrons, right? Because oil rate, right? So losing 8 electrons, which means that they are products. I think the number one mistake people make is they put the electrons on the wrong side. Easy enough mistake to make, right? But you gotta make sure the electrons go on the right side. Now what's the next step? Add H plus to balance the charge, right? So in the first half reaction, what's the charge on the left side? Over here. -2. And on the right side, it occurs to me I didn't actually put a negative sign on them, or electrons. -10. So what do we need to balance it? How many H pluses? Yeah, 8 H pluses on which side? The right side. Okay. So then I'm going to go up here and I'm going to add 8 H pluses, right? But then what we need to remember is that OH minus does what with these? Turns them into H2Os, right? So 8 H pluses on the right side are going to become 8 H2Os on the right side, right? And what else? And 8 OH minuses on the left side. Does that make sense? So So I'm actually going to add my 8 waters here, and then I'm going to put my 8 OH minuses on this side. Does that make sense? And then we're almost there. What's the last step? Water to balance. And we can quickly look to see if we need it. And I think we do need it. How many do we need? Let's count. H2O on the left, or just let's count. H is on the left. 8. H is on the right. 16. So where do we need? How many waters and where? Not 8 waters. 4 waters, right? So 4H2O here. And of course, what does that actually just do? Yep, it balances. It should balance everything. But what do we note? Why did I write it in red? Because it's going to cancel, and it's actually going to turn this into how many? 4. Does that make sense? And now we have our first half reaction. Does that kind of make sense? And now we can do our second half reaction, which is what? And let's just quickly make sure this balances, by the way, because it's easy to make a mistake. 8 oxygens, and over here we have 4 from the water, 4 from the SO4, giving us a total of 8. Awesome. We have 8 hydrogens, and here we have 8 from the water, so that's good. We have 1 sulfur, 1 sulfur. Awesome. What's the charge over here altogether? On this side? -10, right? -10. And over here? -10. So we're balanced. Does that make sense? But it's never a bad idea to double check and make sure you haven't screwed up. Because sometimes you screw up. What's the second half reaction? Diatomic iodine yields iodine ions. Okay, and we'll go again. First step, just balancing the key elements. What do we need to do that? Very good. So we need 2 there. Okay. Next, we need to add electrons. So let's look for iodine. What's its oxidation number on the left side?
0.
What's its oxidation number on the right side? -1. So what's the delta? Nope. -1. Good. So is it gaining electrons or losing them? So it's gaining 1 electron per iodine. And how many iodines do we have in this thing? 2. So it's gaining how many electrons? 2. Which side are those going to go on? The left. 2 electrons. Good. Okay, how's that? Next, add H plus to balance the charge. What's the charge on the left? Okay, what's the charge on the right? Okay, good. Add water to balance. Oh, not needed. So this is balanced. So now we can put these together, except we need the electrons to match. So what do we multiply this whole thing by to make the electrons match?
4.
All right. We need to multiply this by 4 so the electrons match. And when we do that, we can just put it together at the bottom, and we can say, okay, I'm going to put it here. Let's go, starting at the top. We have 8 OH minus, right? Plus S2 minus. And then next on the bottom, I'm multiplying this by 4. So I could put 8 electrons. Do I actually want to put 8 electrons? Why not? Because they're going to cancel. But what do I put next? 4 iodines. Good. And then on the other side, let's go. What am I getting? SO4. And then I could write plus 8 electrons, but am I writing that? Why not? They canceled. What do I put next? 4H2O. Oh, not 4,2O. Plus 2 negatively charged iodines. And That should be it. That should all balance. Now we can quickly check it, and then we can put our states of matter in. How many oxygens on the left? How many on the right? 8. 4 there, 4 there. Cool. How many hydrogens on the left? How many hydrogens on the right? Cool. How many sulfurs on the left? How many sulfurs on the right? Cool. How many iodines on the left? And then what did I forget to do over here? Multiply it by, which means this should be 8. See, this is why we check our work. I'm going to pretend that was on purpose, but it wasn't on purpose. I just wrote what you told me to write. Cool. So that all balances. What's the total charge over here? Negative 10. What's the total charge over here? Okay. So are we good? Yeah, we're golden. And so that's a balanced reaction. Then the last thing to do would be to add our states of matter. That's aqueous. That's aqueous. That is a gas, I think. Oh, it's a solid. Solid iodine. Why do I... Hofbrinkel. Iodine can be a gas, but iodine at room temperature is a solid. And almost never a liquid. It sublimates. All right, there we go. So whether you like that method more or what we learned yesterday more is totally up to you. I do want you to practice both, because you might find that once you get a little bit better at one or the other, you like it more. But I rarely teach two ways of doing something. But in this case, you really will come across both, so I want you to be aware of both. The other thing is I really think there are times when half reactions are much quicker, and I think there's times when the other method is quicker. Which you use, up to you. Totally up to you. Yeah. Again, I hope I didn't lead you astray by showing you how to do it all in one step there, but it's just never my tendency to actually write the same thing over and over again, because I think A, it just takes way longer, and B, it makes me more likely to make an error, accidentally copy something wrong. Questions about that? All right, there's some practice there. I commend it to your good learning and work, my friends. Get your practice in. All right, it's very important. We're going like a racehorse here. Now, culminating. We're going to talk. You're going to write me a lab report on any lab we've done. You can pick your one, formal lab. You should all be familiar with my formatting for formal lab, but I'm going to remind you of it tomorrow. All right, so I will walk you through it. It's not going to be due until the last day of classes, but I'm going to invite you to give it to me if you want by Wednesday of next week, and I will give it an edit and then give you a chance to get it back to me by the last day if you want. Or if you want to just roll the dice and submit it once, you're welcome to just roll the dice and submit it once. You can pick any lab we've done. We haven't done many labs, unfortunately, which breaks my heart, makes me sad, makes me very sad. But that's what it is. So pick a lab we've done, write me a nice formal lab report. I will remind you of our formal lab report stylings tomorrow. That's going to be worth 10% of your final grade, and then worth 20% of your final grade is your final exam. That's it for culminating. I don't do a lab exam in this one. Normally I do, but I'm not doing a lab exam with you guys because that would be patently silly when we've barely gotten in the lab, for which I do apologize. But such is life. But hey, we went to a lot of university fairs and assemblies, so that's good. I'm thankful for that. Yes?
No, last year Ruby helped with the editing. She gave comments.
Yep.
That'll also be happening today or no?
I'll do that. I mean, if Kate wants to, she can, but probably I will do all that. And again, if you want comments and feedback, I'm happy to give them to you. When do you have to have it by for me in that regard? Next Wednesday. All right, that'll be the highlight there. For those of you who want help writing, I'm more than happy to give it. But listen, you know my guidelines. What's my first most major guideline? Even more fundamental than that. The most fundamental thing of all. And guys, I'm not dicking around. We're not plagiarizing. This will be your work. So I'm going to create a document right now. I expect you to work in it. If you do not tell me, oh, I used my Notes app and then I cut and paste in. That's good. I used my Notes app to assign you a grade of 0 and then I cut and paste it in. All right? You will work in the document I provide for you. You will do all of your work in that document. All right? And That's the only place you're going to do any work. All right? That'll be up and ready for you by the end of the day today. Look at me. Not screwing around. Last time I taught this course, 2 people got 0 on this final essay. All right? And I didn't give them a chance to redo it. And I didn't give them I didn't, listen to their parents when they screamed at me, which, by the way, they did, and back down. I stuck to my guns. One person lost a pretty serious scholarship as a result. I didn't feel good about that. But I did it, and I'll do it to you too. I don't care. Do you understand me? If you try to pass somebody or something else's work off as your own, which includes the use of generative AI, what grade will I assign you on this if I catch you? Am I guaranteed to catch you? No. Now, the instupidification of the human race is such that even just trying to value your own intelligence and making yourself wiser, I do not claim that I will catch AI every time. But I'll tell you this, I'll be on the goddamn lookout for it. And if I catch you, I'm not messing around. I'm not going to listen when you cry. All right? They always cry. And it doesn't make me feel good when they cry, but it's not changing what I do. If you don't write this completely and entirely yourself, and I find out that you didn't write it completely and entirely yourself, the grade I assign you will be 0, which is the lowest grade you can get. So that's not a good use of your time. If I were a university professor, by the way, what I would have the option of doing is not only giving you a 0 on this, but if I wanted to, giving you a 0 on the course. And if I really felt like it, I could try to get you kicked out of the school, which happens all the time. Ask Chris Vlode about it. He managed to get a room to himself in first-year residence because a few weeks into class, one of his classmates chat GPT'd an assignment and got kicked right out of school. Boy, that's not a good use of thousands of dollars, is it? I'm not screwing around, all right? I don't like it. And if you're wondering, well, what if I just this or just that? Just write it yourself. You're all smart, capable, intelligent young people. There's no excuse for it, all right? So don't come and make an excuse to me. And again, if you're wondering, part of the reason it takes me forever to edit these things is half the time, I'm Googling, I'm literally searching for every second question. I'm putting them into AI detectors, but I also am looking up every single resource you give me to go, is that a real reference? Because that's how I caught them last year. I'm not going to lie, the AI was good enough that I didn't pick up on the language. The AI detector didn't get it, but when there were 3 fake references in there, I sure noticed, right? So and by the way, if you send me a paper and I'm like, oh wow, you read that in the Journal of Theoretical Chemistry from 2011? How'd you get access to that? Show me that article. I'd love to see your markups on it, right? Like, I'm not stupid, all right? So if you're going to cheat, you better not be stupid either, all right? And a lot easier than being smart enough to get one by me is just writing a paper. We clear on that? All right. Yeah.